Hey everybody, I'm back. Did you miss me? Just a joke. Okay, so as advertised, our next video, which is this video now, is going to be talking about constrained optimization when we have constraints on something like production capacity. And so how we do this is using a technique of Lagrange multipliers. So how does that work? Well, we're going to talk in this video about problems with one constraint. Next video will be problems with two constraints, so that'll be the short video actually. Let's let f and g be functions of, so let's say, two variables that have continuous partial derivatives. At every point of some open set containing the smooth curve g of xy is equal to 0. So we need to make some assumptions. First, that f, when it gets restricted to points on the curve g of xy equals 0, has a local extremum at the point x sub 0, y sub 0. And the second assumption is that the gradient of g at that point is not 0. And if that's true, there's a number lambda, that's the Greek letter lambda, called a Lagrange multiplier, for which the gradient of our function f at that point is equal to lambda times the gradient of the function g. So why is this true? A quick sketch. Let's suppose we have a constrained extremum occurring at the point x sub 0, y sub 0, and assume that the equation g of xy equals 0 can be smoothly parameterized using, let's say, x equals x of s and y equals y of s. So x and y are functions of s, s being the arc length parameter. And the reference point is x sub 0, y sub 0 at s equals 0. So then z is equal to f of x of s comma y of s, and that's going to have a relative maximum or minimum at s equals 0, which is going to imply that dz ds equals 0 at that point. And then we use the chain rule to compute dz ds, right? It's the product of the gradient with the vector x dx ds dy ds, right? So at s equals 0, that vector, the dx ds dy ds vector, that's just the unit tangent at the point 0, right? It's the tangent vector to the constraint curve. And so what that means is that the gradient of f at that point x sub 0, y sub 0, dotted with the tangent at 0 is equal to 0. So either the gradient 0 or it's normal to the constraint curve. Now, please notice that when we're saying the gradient 0, we mean the 0 vector, not the scalar 0. So it's normal to the constraint curve at a constrained relative maximum. But the constraint curve g of xy equals 0 is a level curve for the function g of xy. Remember what a level curve is from earlier. So if the gradient of g is not the 0 vector, then the gradient of g is going to be normal to the level curve at x sub 0, y sub 0. And so what that means is, since both of these gradients are normal to the level curve, they have to be constant multiples of each other. So how do we solve these problems? So what we're going to do is we're just going to determine the objective function f of xy, that's the function that we're going to maximize or minimize, and the constraint function g of xy, and then we're going to solve a system of equations. We set the two gradients equal to, well, not equal to each other. We set the gradient of f equal to lambda times the gradient of g, and g equaling 0 at x sub 0, y sub 0. The largest value of f at x sub 0, y sub 0 is the max, and the smallest value would be the minimum. And that's all she wrote. So I really want to spend most of the video time doing a couple of examples. So let's find the maximum of the function 5x minus 3y subject to the constraint x squared plus y squared equals 136. Okay, so we can write the constraint because we want to write as g of xy is equal to 0. So we can write it as x squared plus y squared minus 136 equals 0. And so our g of xy is just going to be that function on the left. Next, we need to find the gradients of f and g. So the gradient of f is just the vector 5, negative 3. And the gradient of g is going to be the vector 2x, 3y. So since that's true, we have to solve the system. So we're looking at gradient of f equals lambda times gradient of g, but that gives us the vector 5, negative 3 is equal to lambda times the vector 2x, 3y, and g equals 0. That just gives us our original constraint equation. Okay, so what system of equations do we get? So the corresponding components of our vectors have to be equal. So the first component on the left is 5, and the first component on the right is 2 times lambda times x. The second component on the left is negative 3, and the second component on the right is 3 times lambda times y. So that comes from the first equation, and then the second equation doesn't actually change. I mean, the third equation is still our constraint equation. Okay, so lambda cannot be 0. We can see that very quickly because if lambda were equal to 0 and we put that into the first equation, we get 5 is equal to 0, which is, usually not good. So lambda is not equal to 0, so we can divide the first two equations by lambda. And if we do that, we're going to get that x is 5 over 2 lambda, and y is equal to negative 3 over 2 lambda. Well, I guess technically we're going to divide by the constant times lambda. It's not negative 3 over 2 lambda, is it? Nope. It's negative 1 over lambda, right? Wait, what did I do wrong? Oh, that's what I did wrong. By the way, make sure when you do these problems that you don't screw up. So those should be 2's. So you might want to take a moment and pause the video and correct what you wrote, unless you wrote it correctly the first time. So I'm going to divide the first equations by 2 lambda, which apparently I subconsciously knew because I started writing everything right. Meanwhile, back to the problem. So here we go. We have x is equal to 5 over 2 lambda, and y is equal to negative 3 over 2 lambda. So if we plug that into the third equation, we can solve for lambda. So I'm going to get 5 over 2 lambda squared plus negative 3 over 2 lambda squared equals 136. 25, 9, 34 over 4 lambda squared is 136. Although technically that's 17 over 2 lambda squared is 136. So 2 lambda squared is going to be 17 over 136, which is 1/8. And then that tells me that lambda squared is 1/16. So lambda is going to be plus or minus 1/4. Okay, so if lambda is positive 1/4, then when we plug it in, we're going to get x is equal to 10 and y is equal to negative 6. And f evaluated at 10, negative 6 is 68. If lambda is negative 1/4, then x is going to equal negative 10 and y is going to equal positive 6. And if I evaluate f at negative 10, 6, I'm going to get negative 68. Since we were trying to maximize the function, I'm going to go with the first one. So, therefore, the function is maximized at x equals 10 and y equals negative 6, and the maximum value is 68. So you might think of this as actually, I'm trying to decide how much of my product to make, and I'm constrained by that weird equation somehow comes up into things. And so I would come up with, what to make to maximize profit or something like that. Okay, we can also use this in a sort of geometric problem. So let's find the point or points on the circle, x squared plus y equals 80, that is or are closest to the point 1, 2. All right, so we need to basically solve a distance problem. We need to minimize a distance, the distance from the point to some point on the circle. Well, the distance, I'm going to call it d of xy, from any point xy to the point 1, 2 is going to be, well, it's the square root of the quantity x minus 1's quantity squared plus y minus 2 quantity squared. But if I'm minimizing this, that's the same as minimizing the square of the distance, which is much more friendly to work with. Don't you agree? Because think about taking the partial with respect to x of that function. So I'm going to define f of xy to be the square of the distance, or the quantity x minus 1 squared plus y minus 2 quantity squared. And our constraint, so what's this going to be? So we're going to minimize this function f subject to the constraint that we're on the circle. X squared plus y squared equals 80, which we can write as, just like we did in the previous example, x squared plus y squared minus 80 equals 0. So g of xy then is going to be x squared plus y squared minus 80. All right, let's do this. Since the gradient of f, well, I'm just going to drop the xy, make it shorter. Gradient of f is going to be the vector 2 times x minus 1, 2 times y minus 2, and the gradient of g is going to be the vector 2x, 2y. Right, to find the minimum, we need to solve the gradient of f is lambda times the gradient of g, or those two vector, the vector grad f is lambda times the vector grad g, and g is equal to 0, so x squared plus y squared is equal to 80. And so this gives the system let's see, so equating corresponding components, we get 2 times x minus 1 is lambda times 2x. we get 2 times y minus 2 is lambda times 2y. And well, the third equation is still the constraint equation. Okay, so this time we have no reason to believe lambda can't be 0. But we do know that x can't be 0. Otherwise, x is not 0. Otherwise, the first equation would be -2 is equal to 0. And similarly, we know y is not equal to 0. So we can solve the first two equations for lambda. Notice that this is a different approach than we took previously. So we can solve the first two equations for lambda. We're going to get lambda is 2 times x minus 1 over 2x, which is just x minus 1 over x. And lambda is equal to y minus 2 over y, 2 times y minus 2 over 2y, which is y minus 2 over y. Therefore, what we have is x minus 1 over x equals y minus 2 over y, cross multiply. X minus 1 times y equals x times y minus 2. Do some algebra, we get xy minus y equals xy minus 2x. So we get that y is equal to 2x. And we're just going to substitute this into the constraint equation and solve for x. So we're going to get x squared plus the quantity 2x squared is equal to 80. So I get 5x squared is 80, x squared is 16, x is plus or minus 4. And then, so if x is equal to 4, then y is equal to 8. And f of 4, I'm sorry, not f of 4, 8. And if f is if x is -4, then y is -8. So that's a -4 and a -8. All right, so if we just put this on a graph, or just use some logic, we can see that 4, 8 should be the closest one, and -4, -8 is the furthest away. So geometrically, we see that 4, 8 is closest, and -4, -8 is furthest. But let's do the constraint equation. Check by, not the constraint equation, f into f of x, y. So we see that f of 4, 8 is 3 squared plus 6 squared, which is 45. And f of -4, -8 is -5 squared plus -10 quantity squared, which is 125. So therefore, we get that 4, 8 is the point closest to 1, 2, and the distance between them is the square root of 45, or 3 times square root of 5. I'm going to sneak in one last problem. Actually, I have more than one problem. I'm actually going to call it a video, and we'll do the next two examples on the next video. So I'm going to stop recording and